So if you're watching this video, then hopefully you've had an opportunity to first watch the video from 3 Blue, 1 Brown that goes over the concept of a Taylor series. And if you haven't watched that video yet, I want you to stop the video right now and watch that 3 Blue, 1 Brown video first. I will link it in the description below because it just does such a fantastic job of breaking down the intuition for how a Taylor series is constructed and where it comes from, and how it's not just some random formula that we need to suddenly memorize, but it is something that makes complete sense and it's logical, and it quite honestly does such a powerful job in approximating the value of complicated functions um, in the neighborhood of a chosen center. So if you haven't watched that video, please watch that video first, answer these questions, really think about that, think about it. Maybe you want to watch it more than once, but definitely watch that video if you haven't already done so. In this video, I simply want to review the main concepts of a Taylor series and a Maclaurin series, and just work with you on a couple of practice problems to really make sure we understand the structure so that we can start diving a little bit deeper into some of the benefits here. So again, a Taylor series is a way of modeling a function in the neighborhood of a chosen center, which we will describe using the variable c. And this function must have a derivative of all orders. So we have an nth degree Taylor polynomial. So we can say, all right, we can represent this function f of x using a Taylor series. And the Taylor series is simply the summation of all terms generated by this general term. Now, we have a Taylor polynomial and we have a Taylor series. The only difference really being that a Taylor polynomial is finite. So you can think of it as like a partial sum of a series, whereas a Taylor series is infinite. So a Taylor polynomial is often used to give us a really good approximation of what the function is doing. A Taylor series gives us exactly what that function is doing. And that's one of the coolest things about it, is that a Taylor series is exactly that function. A Maclaurin series is simply a specific type of Taylor series. It just, when the center of the series, or excuse me, when the center of the function is at x is equal to 0. So if we're looking at this carefully, we're going to use these here to help us generate some Taylor and Maclaurin series in some of the examples below. So let's get started. So let's start with this first problem here. And you're going to see me switching back and forth from some colors because I think it'll help us make sense and keep track of all that we're doing here. So we're going to create a Maclaurin series for the function sine of x. So our function is sine of x, right? Basic trig function, and we're going to find its appropriate Maclaurin series. And we're going to use the interval of n from 0 to 5. So what I often do is set up a table to help me keep track of everything that we're doing here. So I'm going to start with n is equal to 0. Now, first, I want to make sure that we highlight if n is equal to 0, that means we are going to be raising this x, to the 0 power. That means all of this here is going to be equal to 1. Anything raised to the 0 power is 1. So in other words, this first row is going to help me come up with my constants, because you're just going to be multiplying a numeric value in a moment by 1. So what is the 0th power of, or 0th order derivative of our function? Well, that's just sine x. So in other words, we're not taking the derivative yet. We're just writing the function itself. Then in the final column, what is that 0th order derivative, or what is that function now? Simply evaluated at 0. I'm just asking you, what's sine of 0? And that would just be equal to 0. So our constant is going to be 0. Now, in this next column, I'm going to switch to a different color here. In this next column, or row, I should say, n is equal to 1. Now, we are then going to be finding the first order derivative of sine, which is cosine x, the first order derivative of sine, which is cosine x. And now we're evaluating cosine of x at 0. So cosine of 0 is 1. Okay? And let me do one more row before we start to see kind of how we are putting this all together. So let me go n is equal to 2. Okay, this is the next row, n is equal to 2. Now I'm going to do my second order derivative, or my second derivative of sine, which would be negative sine x, right, which is just the derivative of cosine. Now, what is negative sine of 0? We're evaluating the second order derivative at 0, which is going to be equal to 0. All right, so I'm not done yet, but I want to start building this Maclaurin polynomial for you, just so we can get a sense of what we're actually building right now. So I'm going to say the following. I'm going to say this polynomial consisting of the first, well, technically it's the 6 terms because we're starting at n is equal to 0, but going up until n is equal to 5 of x, okay? So we're going to start by finding the Maclaurin polynomial, and then I'll finish up by actually writing the Maclaurin series here. So our first term, our constant, was 0. Then I'm going to use that first order derivative evaluated at 0. That's going to represent our coefficient times x to the 1 power, because n is equal to 1, x to the 1 power over 1 factorial. And again, I am using this here. I'm plugging in and I'm writing all my terms based on this. So that coefficient is that first order derivative evaluated at 0 times x to the 1 power over 1 factorial. Next up, now I'm going to go ahead and use my next row. So that's my second order derivative now evaluated at 0, which we said was 0, times x to the second power, because n is equal to 2, over 2 factorial. And we're going to keep doing this. So let me finish up the table first, and then we'll finish up this polynomial. But I just wanted to pause and have you see exactly what we were generating now. So let's go to a different color. Let's say, let's make this blue. So when n is equal to 3, the derivative of negative sine x, or my third order derivative, is negative cosine x times, and that third order derivative evaluated at 0 is going to be negative 1. And then let's switch to orange. When n is equal to 4, the derivative of this is going to be sine of x. Sine evaluated at 0 is going to be 0. And then for our last row, when n is equal to 5, the derivative of sine, we're now back to cosine x. Cosine evaluated at 0 is positive 1. So plugging in what we know. So I'm going to have to keep track of this here. All right, we got our third order derivative evaluated at 0 was negative 1. So we're going to write negative 1 here, times x cubed over 3 factorial, plus our fourth order derivative evaluated at 0, which is just 0, x to the 4th over 4 factorial, and then plus my fifth order derivative evaluated at 0, so that's just 1, times x to the 5th over 5 factorial. Okay? Now, keep in mind, there is a finite number of terms. This right here is my Maclaurin polynomial. It's my polynomial. It is finite. But the problem asks us to find the Maclaurin series. Well, that just means I'm going to express this function, sine of x, f of x, is equal to the following series. And I'm just going to clean this up just a little bit. Our first term was 0, so we don't have to write that. We can just say x over 1 factorial, which is just x. And then next up, we've got another term with a 0 as its coefficient, so that means we can just skip over that, minus x cubed over 3 factorial. Skip over the next term here with 0 as its coefficient, then just jump right to x to the 5th over 5 factorial. And if I just ask for the series, I could stop here. This is my Maclaurin series, right? And I stopped with enough terms that I could show, given that the problem asked me to go from 0 to 5 for my n. If the problem then also asked for the general term, which this problem doesn't, but I'm going to walk you through how we would do that right here. Again, this is just us trying to come up with a general term based on what we're seeing from all of its previous terms. I see that the series is alternating, so I'm going to say -1, and since my first term, that as I've written it right now, is positive, I'm going to make this n minus 1. And looks like I'm taking all of my x's to the power of, well, let's see, when n is equal to 2, I get 3. So this would be 2n minus 1. And all of this, I see that there's a connection between the degrees and what my denominator factorial is. So I can just say that this would be 2n minus 1, all of that factorial. Okay, so there's my general term. So again, I've got to make sure I write this to indicate that my series is infinite. But this infinite Maclaurin series is exactly equal to sine of x. And as we've discussed earlier, there's a lot of benefits to this. Us being able to work with the calculus of the series oftentimes is far more approachable than working with the calculus of a transcendental function like sine of x. So hopefully that helps give you a sense of how we would build a Maclaurin series for sine of x. Let me do one more example with you. Let's now use the definition of a fourth degree Taylor polynomial. This time we're just going to be working with a polynomial. And we're going to see that this Taylor polynomial is centered at x is equal to pi. And we are going to write the Taylor polynomial for cosine of x. And we're going to use our Taylor polynomial to actually approximate the cosine of 3. Okay? So first things first, let's build the polynomial. So it's asking for a fourth degree. That means we're going to go all the way to n is equal to 4. So we're going to start out at 0. So at 0, we've got the function itself. So the 0th order degree derivative, the 0th order derivative is simply the function itself, cosine x. And we're evaluating that function at the point where it is centered. In this case, it is centered at pi. So cosine of pi is going to give me -1. Next up, when n is equal to 1, now we're on to the derivatives. We're going to move on to our derivative. Our first derivative is negative sine x, and that first derivative evaluated at pi is 0. Next up, when n is equal to 2, we have the derivative of negative sine x, which is negative cosine x, evaluated at pi is 1. N is equal to 3. Sine of x now, evaluated at pi is 0. And then finally, when n is equal to 4, we're now back to cosine x, evaluated at pi is -1. So now we're going to build our polynomial. So our fourth degree polynomial, meaning when n is equal to 4, is the following. And so I'm going to write out all the complete terms and then we'll clean it up a little bit. Remember, our first row always gives us our constant because when n is equal to 0, we're raising x to the 0 power, which is just 1. In this case, times -1. So we've got -1. Now, moving into our next row, we've got 0 times x minus pi raised to the 1 power all over 1 factorial. And again, I'm using this right here. Okay. Well, I should say technically, since we're doing a Taylor series, I actually should say we're using this right here. Okay. So that order derivative times x minus c raised to the n power over n factorial. So you can pause there and compare the two, but I'm going to move on now. So going back to this, we can then say, I'll just move on to this next row so I don't run out of space. We've got now 1 times x minus pi squared over 2 factorial plus 0, and I'm thinking I'm going to run out of space, so I'm going to just make this a little bit smaller so I have some space to work with, plus 0 times x minus pi cubed over 3 factorial. Finally, plus -1 times x minus pi to the 4th over 4 factorial. And since this is a Taylor polynomial, which consists of a finite number of terms, I can stop there. But I want to clean that up a little bit. Might as well write the actual Taylor series. Now, this is the Taylor series that I'm about to write right now. And I'm just going to clean this up. I'm going to say, all right, my first term is my constant, -1. This next term here, I can just pretty much skip because these both have zeros for their coefficients. So I can then move on to writing x minus pi squared over 2 factorial plus, or I should just say minus, my next term is negative, minus x minus pi to the 4th over 4 factorial, and so on. And this infinite number of terms indicates that it's a series here. Now, just to finish this up, I've just written the Taylor polynomial for this. Now, it's asking me to use my Taylor polynomial to approximate the cosine of 3. So let me just do this in a different color. So cosine of 3, remember, our function is cosine. We're going to try to evaluate cosine of 3, and we're going to use the Taylor polynomial to do that. So we're going to say, all right, let's say that this cosine of 3 is approximately equal to the 4th degree Taylor polynomial evaluated at 3. So what we're going to do is we're going to plug 3 into what we have for our 4th degree Taylor polynomial. Well, that's -1, which is our first term, plus our x now is being replaced by 3, so 3 minus pi squared over 2 factorial, minus 3 minus pi now to the 4th over 4 factorial. And if we punch that into our calculator right now, just to see here, if we punch that into our calculator, we should get approximately -0.9899992. Well, let's just take a quick moment and just compare that to what the cosine of 3 actually is. Well, it's really darn close. It's probably off by maybe the 7th decimal place or so, but that is what we get there. So it's an incredibly good approximation for what the cosine of 3 actually is. We have that there, okay? So again, this wasn't a conceptual breakdown of how we arrive at these structures for a Taylor and Maclaurin series. Again, I highly, highly encourage you to watch the video for that, the 3 blue, 1 brown video. But what hopefully you were able to get out of this is a recap of how we can use Taylor and Maclaurin series to approximate functions, and also how to generate the actual Maclaurin and Taylor series. So go ahead and try these practice problems below. And again, check my scanned notes in Google Classroom to give you a sense of how accurate we are with our approaches here.